Hello, fellow participants of the Combinatorial Optimization Network 2020. On the 7th day of the summer school, we discuss problems in the context of transit planning and scheduling. We will give you an overview of the whole planning process and also focus on some specific problems with an optimization point of view. This lecture will be given in 3 parts. First, I will give an overview of the planning process in transport systems and also discuss path optimization problems. The second part belongs to Ralph. He will talk about optimization problems concerned with vehicles and crews. Finally, Louis is talking about a particular problem that integrates vehicle and pollster scheduling. It's quite clear and requires no convincing effort that public transport systems makes up the base of the urban life, as it is the main medium that allows people to flow and wander within and around the city. As the city life gets more complicated, the transit system becomes even more significant in satisfying the needs and maintaining the comfort of the inhabitants. In this respect, such systems should be fast and efficient while they sustain reliable and comfortable operations. Various modes of transportation should be connected and linked with each other. In addition, the side effects of such big systems, such as pollution and energy consumption, should be under control. Such goals can be simultaneously achieved with the best use of data and information. And this is actually where mathematics and indeed operations research comes handy. A traditional approach for planning in public transport systems has 3 main phases and various stages. This approach is usually considered as sequential planning. The very first phase is considered as service design, which involves planning and designing the infrastructure, including the establishment of the facilities. Once the infrastructure is fixed, the next stage is involved with determining how the transit service is to be provided using this infrastructure. This stage is also known as line planning, since the lines that specify the service is made up at this stage. When line plans are fixed, the Public Transit Authority determines the timetables of the service provision based on the expected demand on the lines at different days and different times of the day. This is actually where the second stage, which means operational planning, starts. The timetabling is followed by vehicle and crew scheduling so that the operational requirements of the services are provided. The final phase of the plans are involved with operating the plans and ensuring that the necessary resources are made available at the right time and at the right place so that plans can be executed finally. And both the plans and information regarding executions are shared with passengers. In response to this information from the Public Transit Authority, passengers make their plans and decisions in order to make best use of the provided services. Naturally, this planning approach may be modified from one company to the next depending on their aims and goals, and also their business understanding. For instance, market plans and demand forecasts are also considered as part of the planning process at Deutsche Bahn. IBU Traffic Technologies, a software company providing solutions to transit and transportation systems, again take the sequential approach. They provide software tools for various stages of planning, including some of the problems we have mentioned, and also some additional decision support and control tools. Similar approaches are valid also for large-scale transport systems such as airlines. For instance, Lufthansa systems consider the integration of aircraft and crew scheduling in a similar sequential understanding, where the whole planning process embodies various stages of decisions that span both planning and control of the operations associated with both crew and schedules in an integrated manner. To start with, we will take an upside-down approach. Let us assume that the public transit system, having gone through all stages of planning, has already published their service schedules, and passengers with transit demand are expected to determine how to make optimal use of the provided services to go from an origin to a destination. Let us assume that our passenger is already at Alexanderplatz and wants to go to zip. The main information the passenger requires is the main transit network, which is indeed shown on this map. And on this network, the passenger wants to find the shortest path from Alexanderplatz to zip with respect to the number of stations to go through. Once we represent the transit network with a graph like this, it turns out to have 306 nodes and 445 edges. Now the passenger problem turns out to be a shortest path problem from the node representing the Alexanderplatz here to the node representing the zip. And indeed, the solution of this problem is highlighted with the yellow path here. Let us now look at the shortest path problem closely and investigate how it can be solved and understand how it would or would not be a combinatorial optimization problem. As it is also the case in our example, we are talking about a single source shortest path problem. The problem can be defined either on a directed or undirected graph with weights on edges. The length of the path is the sum of the weights of the edges on the path. For a given source S and destination T, here, the shortest path problem selects the minimum length path among all paths from S to T, as shown here. Some versions of the shortest path problem has simple optimal solutions. Simplicity in this respect refers to no repetition on the path, no repetition of the nodes on the path indeed. For instance, for the conservative shortest path problem, there are no directed cycles, which has a negative cost. So the shortest path, the optimal path indeed, can be found as a path with no repetitions of the nodes. The same property applies when triangular inequality holds for the distance metric in use. This inequality, as shown here, implies that going from U to V, going from U to W, is always shorter than going through some other node V. For instance, the Euclidean metric is one such example. For the graphs with non-negative edge weights, which is usually the case but not necessarily always, Dijkstra's algorithm is a well-known method to find the shortest path. This algorithm uses a spatial data structure called distance labels. The algorithm finds paths originating from the source to all other nodes by expanding a path with one more edge in each iteration. During the algorithm, the distance label of a node shows the length of a shortest path from the source node to that node at that time. As new paths are found, the distance labels are updated to reflect the length of the new shortest paths. At the beginning of each iteration, here, the algorithm finds the node with the minimum distance label and scans all of the arcs, as shown with this for loop, emanating from the selected node. And possibly, the labels of the nodes that are the heads of the scanned arcs are updated accordingly by the newly calculated distance labels. Once a node is selected and used to update some other labels, it is never selected again because it cannot have the minimum distance label. That's one of the key properties of this algorithm. So this also means that the algorithm overall makes n iterations, which is equal to the number of the nodes. So it makes n selections, as we do here in line 3. Okay? This means, in terms of the time complexity of the algorithm, if a minimum label can be selected in log n time, the node selection throughout the algorithm can be executed in order of n times log n time. Each time a node is selected, the arcs emanating from this node will be scanned. So this also means that an arc is scanned only once, or the distance label is updated with respect to an arc only once. So overall, the distance updates that are within this for loop will be conducted in order m time. So the complexity of the algorithm, the overall complexity of the algorithm, turns out to be order of n log n plus n. Also, we can talk about the correctness of the algorithm shortly based on how the algorithm progresses. Now, the main idea here is that the algorithm selects the minimum distance label at each iteration. And because the minimum distance label is selected at each iteration, the distance labels are correctly updated only when necessary. This also proves the correctness of the algorithm. But for the sake of time, I'm not going to spend too much time here. You can go to the infamous network flows book by Ahuja, Magnanti, and Erlin, and they have a very concise and clear proof for this argument. Now, let us get back to our example from Alexander plots to zip. It is clear that the Dijkstra algorithm will run faster when the number of nodes and edges are smaller. So we first reduce the size of the network by getting rid of the nodes that are adjacent to only two other nodes. The transit network goes from 306 nodes to 80 nodes, and from 445 edges to 122 edges only. We then start the algorithm at the node representing the Alexander plots. First, the distance labels of the nodes that are only one edge away from the source node are updated. Once this update is done, the node with the minimum label is selected. And the labels of the nodes at the head of the emanating arcs are updated. In the same fashion, the paths are expanded by selecting the minimum distance label after each update, until there are no further distance labels to be updated. Finally, a path from Alexander plots to zip is found, while the distance label of the node representing zip is 10, which corresponds to the number of stations to pass on this shortest path. It is clear that we can solve the problem efficiently under certain conditions, as it is the case for non-negative edge weights and the Dijkstra's algorithm. How do we generalize the representation of the problem with a mathematical model? First, we need a binary variable to determine whether an edge is included on the path or not, as shown with x here. In this model, the objective function sums up the weights of the selected edges. In order to find a single simple path that originates from the source node, here, the formulation enforces only one edge emanating from the source node to be selected as seen in the first constraint, while all other nodes, excluding the destination node, has perfect flow conservation. Well, is this problem, as an integer programming problem, difficult to solve? Now I would like you to remember what we have learned on the first day of the lectures. As you might remember, not all integer programming problems are difficult to solve. Shortest path problem is one such example. When the integrality constraints are relaxed, the convex hull of the integer problem is equivalent to the polytope of the LP relaxation. As a result, the problem can be solved as a linear programming problem. There are many applications of the shortest path problem and its variants. The flight trajectory planning is one such example that includes many additional restrictions in addition to the main flight sector restrictions that are known as spatial flight regions in the air. Depending on the additional challenges and particular conditions specific to the problem, the requirements of a good algorithm may change. For instance, Let us take the example of finding the best flight trajectory from Berlin Tegel to Dubai. If we implement the traditional Dijkstra algorithm on the graph representing all available flight sectors, the algorithm will explore many partial paths, most of which have nothing to do with the shortest ones. As you see in the current example, the paths expand even in directions that have nothing to do with the trajectory from Berlin to Dubai. A version of Dijkstra's algorithm considers additional closeness restrictions of the explored paths to the destination, which helps reducing the number of explored nodes and edges. Here we see with the yellow path trajectories, the implementation of the A-star algorithm. The superoptimal wind algorithm, on the other hand, even considers the effect of winds and the time of the day on the duration of the flight on even a further restricted graph. From this example, we can see that different requirements and restrictions of the problem may yield different versions of the algorithm. In the same context, we can look at the Taipei-New York City flight plan. In this example, having multiple criteria to be optimized is the main challenge. While the flight distance seems to be the most obvious criterion, the shortest path in distance from the origin to destination may not be the shortest path in duration, not necessarily the minimum cost or the most environmental friendly path. For this particular example, a traditional heuristic would find the shortest path as the red one here. However, a more sophisticated heuristic that considers the effect of oceanic jet streams on the flights finds this green path, which is longer than the red one in distance, but saves time, fuel, and reduces cost significantly. Therefore, in practice, the shortest path problem may not be as simple as that of the public transit passenger. There are usually additional restrictions that are reflected as constraints in the models, which introduces a new class of problems as constrained shortest path problems. In general, this class of problems is not necessarily as easy as the simple shortest path problem. It is NP hard, and the LP relaxation will not help solving the IP problem. Even for the supposedly easier spatial case on an acyclic graph with non-negative costs, the problem is still NP hard. Let us look at this spatial case a little closer and call this problem acyclic constraint shortest path and name it as ACSP. For an acyclic graph, we can find the topological sorting of the nodes and index them in a way that the tail node of an arc has a smaller topological index than the head node. For an arc UV, it means the index U is smaller than the index V. In this example, the node indices are given in accordance with the topological order. We want to find shortest paths with respect to costs, denoted as C for each edge, and as an additional constraint, the total weight of the selected arcs, shown with A, should be at least 6. Let us focus on a search algorithm that keeps tracks of the distance labels in the Dijkstra algorithm together with the total weights of the arcs on the path. This is indeed a dynamic programming algorithm, but you can also visually track the progress of the algorithm on this table. The table rows correspond to the nodes on the graph, while the column indices show the total weight of the path. The table entries show the length of the path in progress. We start at node 1 with a weight of 0 and path length 0. Let us take a minute to let you watch the progress of the algorithm. Finally, we find the path 1, 2, 5, 8, 9 with a length of 10 and the total weight of 6. The only drawback of this algorithm is the runtime, unfortunately. The size of the table is dependent on the maximum possible total weight of a path, which is not necessarily a function of the graph size. Please pause the video here and take a few minutes to understand the terms in the computational complexity term. We now look at a more generalizable algorithm that can be used for optimization problems in various forms. Lagrange relaxation or Lagrangian relaxation can be applied to optimization problems in the following form. We minimize a linear objective function over a set of linear inequalities. For example, they can be represented as dx equal to d. And another set of very general constraints that we may denote by x. The only property that we require is that x is closed. We suppose that x in x are tractable and we know how to optimize over them. They might be linear constraints or combinatorial ones. However, the equations dx equal to d make the problem more complicated. One way to deal with these complicating constraints is to move them into the objective function. For this purpose, we compute the slack in the constraints and subtract it from the objective, penalize any violation by a so-called Lagrangian multiplier. If some constraint is violated, the slack is negative and subtracted. We can choose a positive multiplier to penalize the violation in an attempt to move the solution towards more feasibility. For any fixed penalty vector of Lagrange multipliers, the resulting problem in which the complicating constraints have been moved to the objective function is called a Lagrange relaxation of the original problem with respect to the constraints dx equal to d at the multiplier vector lambda, as shown here with L problem P dx equal to d of lambda. If we assign to each multiplier of the objective function of the associated Lagrange relaxation, we obtain the Lagrange function of the problem with respect to constraints d. If these constraints are clear or the problem, we also leave them out of the notation, as shown here in this part. The main property of a Lagrange relaxation is that it provides a lower bound to a minimization problem, similarly as an LP relaxation, as we see in this theorem. Let's denote the optimal objective of the problem of interest by nu p here. As we see here, this is a very similar case to any other relaxation, and in the case of minimization, it is considered as a lower bounding problem. In addition, we can say the following about the Lagrange relaxation. A, the largest of the objective function values of any Lagrange relaxation over all vectors of multipliers is a lower bound to the optimal objective of the original problem. B, if the tractable constraints are linear inequalities, such that the original problem is a linear programming problem, the Lagrange relaxation provides exactly the LP bound. C, if the tractable constraints are inequality constraints, plus there are some integrality constraints, the Lagrange relaxation can be better. We are mainly interested in dealing with complicating constraints in combinatorial optimization problems, which we can view as optimization over polytopes. Finally, in this case, Lagrange function has some nice properties. Namely, it is concave, piecewise affine, and bounded from above. We can now prove this theorem. If you are interested, let's listen to Siri, who will walk you through each statement of the proof.
The first property states that the Lagrange function provides a lower bound for the optimal objective of the original problem. Let us take some vector lambda of Lagrange multipliers and look at the associated relaxation. The Lagrange relaxation lets us optimize over all elements of X. If we only optimize over those that satisfy the complicating constraints, the slack and hence the penalty will be 0. If we optimize over all elements of X, we have all these choices with the same objectives. Therefore, the value of the Lagrange relaxation will be lower. As this holds for every vector of Lagrange multipliers, it also holds for the supremum. Let's next look at the LP case. What happens if we apply Lagrange relaxation to linear constraints? This question can be answered by applying the duality theorem of linear programming 2 times. We start with the original LP. We dualize and maximize over dual multipliers lambda for the complicating constraints dx equals d, and mu for x equals b. We then take first the maximum over lambda, and then over mu. Again, we dualize the part with mu. We obtain exactly the Lagrange function for lambda. In other words, in the LP case, the Lagrange multipliers are exactly the dual variables for the complicating constraints. If an LP and its Lagrangian relaxation coincide in their objective, the Lagrange relaxation gets better if it can treat integrality constraints. So, C is also clear. Finally, let's look at the polyhedral case, in which X is a finite set of its convex hull. In this case, the Lagrange relaxation optimizes for each fixed vector lambda of multipliers over a finite set of points from X for each point. The Lagrange function is affine in lambda, the minimum of a finite number of affine functions, however, is piecewise linear and concave. It is also bounded from above by the optimal objective of the original problem, which is finite, as its solution set is bounded and non-empty.
There is also a version of Lagrangian relaxation of inequality constraints. If you put them into standard form, as here, you simply have to use the non-negative multipliers. The next question should be about finding the correct set of Lagrange multipliers. How do we find the multiplier that gives us the best Lagrange bound? Or in other words, how do we maximize the Lagrange function, or more generally, a concave piecewise affine function? The problem is that such a function is not differentiable at the kinks, such that we cannot use, for instance, the Gauss algorithm of differentiable optimization, which follows the gradient. However, there exists a suitable generalization of the gradient, namely the subgradient, and the subgradient method will follow such a subgradient. What is a subgradient? Well, for any concave function at any point lambda, the subgradient is a vector that provides a linearization at lambda that overestimates the function, like this or like this. So there might be several subgradients at any given point. The set of all subgradients at some lambda 0 is the subdifferential of function at lambda 0. Similarly to differentiable optimization, we have found that the maximum is 0 and contained in the subdifferential. If the function is differentiable here, there is only one linearization that is provided by the derivative. Hence, the subdifferential contains only the derivative. But we are mainly interested in the polyhedral case. How do we get a subgradient in this case? Well, the answer is very simple. We just compute the negative slack of the relax constraints. This vector is a subgradient, and all subgradients can be obtained in this way. Okay, let's try to prove that now. As earlier, if you want, you may skip the proof for now.
Let us look at some initial lambda. and let x of lambda be those feasible points whose affine functions are tied up lambda. Let ui be the associated supposed subgradients. We first show that any such vector is a subgradient and provides an overestimation of the function. Y is f of lambda 0 plus ujt, lambda minus lambda 0, an overestimation. Well, we can simply calculate that. We insert for function f, and for uj, simplify, and then obtain the affine function associated with the tight solution xj. This clearly overestimates the Lagrange function, which is the minimum over all affine functions. The backward direction is a bit more complicated. We first look at lambda 0 of interest, and add all points xj whose affine function is tied up lambda 0. The other points xi are not tied up lambda 0, and, by continuity of f, also not tied in a small vicinity of lambda 0. Near lambda 0, affine functions that are tied up lambda 0 can be tight. So x of lambda is a subset of x of lambda 0. Let's now take a vector u that is not in the convex hull of negative slacks of tight solutions. We have to prove that u is not a subgradient of f at lambda 0. As u does not belong to the convex hull of negative slacks of tight solutions, we can cut off this point by some separating hyperplane pi. We show that u does not provide a linear overestimator. In fact, we should look at the point lambda 0 plus epsilon times pi. F is defined by a set of affine functions, namely a subset of those functions that are tied up lambda 0, as we proved a second before. Rearranging, we can express the function value in terms of the value at lambda 0, plus an inner product of pi times the negative slacks. However, this product is strictly underestimated, and not overestimated, by the vector u as a result. U does indeed not provide an overestimation.
Now that we know how to compute a subgradient as the negative slack of the complicating constraints, we can formulate an algorithm to optimize the concave function f. This subgradient algorithm is the most simple one that one can imagine. We just start at any initial lambda 0. We compute a subgradient, go some step in this direction, and iterate. How far we go in the kth iteration is an input to the algorithm. The algorithm produces the sequence of these iterates. That's all. Nevertheless, this method works under some very mild assumptions. We first need that the maximum exists. Otherwise, the algorithm can go on forever. We also need some kind of Lipschitz assumption that the norms of the subgradients are bounded. And we need to choose the sequence of step lengths in such a way that their sum diverges. Under these assumptions, the sequence of iterates converges to the optimal. For the proof, let us go back to Siri.
We do not look at the difference of the function value from the optimal objective value, but at the square distance of the iterate to an optimal solution. Let's insert the definition of the k plus first iterate and multiply out. We get the square distance of the iterate k plus some terms that reflect the movement from iterate k to iterate k plus 1. Do that again and again until we arrive at the distance of the starting point to the optimum, and insert the definition of the subgradients to replace the inner products by function differences. Now move the sum of function differences over to the left. Delete the difference of lambda k plus 1 to lambda star, and replace the function differences by their minimum, which is obtained at the maximum objective of the iterates. Now divide by the sum of step lengths. It goes to infinity while the denominators on the right-hand side are bounded. Hence, the function difference goes indeed to 0 and the method converges to the maximum.
Let us illustrate the Lagrange relaxation procedure with our example of the constrained shortest path problem. We know how to compute shortest paths, so this part is the easy part. Only if we did not have the minimum total weight constraint, which is here. The minimum weight constraint makes our life difficult. So we want to relax this constraint in a Lagrangian fashion and put it into the objective function to penalize the paths that are too light, not heavy enough. The complicating constraint is an inequality in standard form. So we use a non-negative Lagrange multiplier. In order to explicitly evaluate all possible solutions of the problem, let us first compute all paths from 1 to 9. There are 6 of them, as we see here. Here we see their costs in the third column. And in this column, we have the total weight for each path. Accordingly, we can calculate the slack values here for the complicating constraints, and the affine functions representing the penalty associated with these paths are displayed here. If we draw these affine functions one by one for each path, P1, P2, P3, P4, P5, and finally P6, we also obtain the complete Lagrange function as shown in red here. That's actually what we want to optimize. Let me give you a moment now to clarify what each path corresponds to and how the Lagrange function is formed. Can we solve our example constrained shortest path problem? Yes, we can. We can do that with the subgradient algorithm. Let's start at our initial value lambda equal to 0. At lambda equal to 0, we see that the tight path is path number 1, and the corresponding objective function value of the Lagrange relaxation is equal to 4. The slack value here is -5, and the subgradient value is 5. With a step length of 1, we can calculate the new lambda value at iteration 1, lambda equal to 1, as 5. When lambda is equal to 5, the corresponding tight path is path 6, and the objective function value of the Lagrangian relaxation is equal to 1. For path 6, the slack is equal to 3, the subgradient is equal to -3. With a step length of 1 over 2, we calculate the new lambda value as 7 over 2. At 7 over 2, the tight path is still path 6, and the corresponding objective function value is 11 divided by 2. With the subgradient of -3 and the step length of 1 over 3, we calculate the new lambda value as 5 over 2. For the new lambda value of 5 over 2, the tight path becomes path 5. And the corresponding objective function value becomes 8. For path 5, the subgradient is equal to -2. And with the step length of 1 over 4, lambda value becomes 2. At lambda 1.6, there are 2 tight paths, number 3 and number 5. If we stick with path 5 and do the corresponding calculations, the new lambda becomes 19 over 15. At lambda equal to 19 over 15, path 3 is still tight. Here, however, the slack becomes 0, which brings the subgradient also to 0. And this is basically proof of optimality. The final objective function value, which is equal to the Lagrange relaxation objective function value also, is 10, The corresponding path is a feasible path, so the solution is optimal. However, remember that in general, Lagrange relaxation provides only a bound and not necessarily a feasible solution of the original problem. This is the end of the first lecture. I hope that you understood how to model some traffic problems in terms of constraint shortest path and how to deal with constraints using Lagrange relaxation. Thanks a lot for your attention, and don't miss the second lecture with Ralph.